Yeah, without much further ado, I would quickly like to introduce Travis. Travis is our speaker of the day, all the way from Nova Scotia, I believe you are in Canada. Travis did his PhD in computational neuroscience at the University of Waterloo. Please correct me if I'm wrong. And then did a postdoc in the same lab as well. And afterwards, with some colleagues together, founded the Applied Brain Research company that he is currently still very much involved in directing. Is that right?
Yep, that's correct. I'm currently COO.
Great. And today we're going to hear about one of their most recent works where they go the full pipeline of from neuromorphic chips to light control. So we're all excited to hear what you guys are coming up with, because we're working on similar projects here.
Awesome.
Thanks.
Yeah, thank you very much for having me and setting this up. And thanks, Serge, for reaching out and suggesting that we put this together. Today I'll be talking about a paper that I put out last year or earlier this year. Time is a blur. I have a 14-month or 17-month-old daughter and another one on the way, so I'm sure it'll get more blurry. But the work was neuromorphic control of a simulated 7-degree of freedom arm using Loihi. And so kind of the core concept in this project, or in the paper at least, one of the things I focused on was like the methodology that we used to approach building a complex, highly complex functionality kind of network. And there were a few stages and heuristics that we used that I outlined in the paper, and I'm not going to focus on all of them, but I'll just overview the 3 stages here, or 4 stages briefly. The first was, we're kind of coming to this problem with an algorithm that we want to implement. And the first step is building out a circuit diagram with like a flow of information between the functions that we need to compute to actually implement this algorithm. And so we're just doing that at a circuit level. We're not using neurons at this point. It's just like Python code in a series of nodes, and we get the information to flow through the network. The second stage then was breaking those, taking each of the nodes with a specific set of functionality and implementing that in rate neurons. Afterwards, we do that same thing with spiking neurons, and then finally we take our network that's now fully spiking and we adapt it based on the constraints of the specific hardware that we want to implement it on. And this will involve taking into account a bunch of things, like usually memory constraints in terms of the bit width of the weights or the connectivity that can be allowed between different layers, all of these kinds of things. And this whole process is really, it's iterative. At each stage, you might be going back to the circuit diagram level, retooling things, making sure everything works, and then going forward again. And so in this talk, though, I'm going to be focusing on the latter half of this process, assuming that we have kind of a rate neuron implementation and talking about the steps of getting this going in spiking neurons and then getting this going in Loihi. So first, of course, the specific problem. We have the Canova Gen 3 arm here. And sorry, I'll also mention all of this work was done with the US Naval Research. Our collaborators there, Joe Hayes and Roxana Leonte, who are both great. And so they have a Canova Gen 3 arm, which is a really nice torque-based control arm that can run at over 1,000 hertz just with your laptop. So it's really an ideal arm for for testing out these kind of force control applications. And the idea is we want to hook this up to a Loihi and have the arm be fully controlled from Loihi. So we're sending the joint angles and the joint velocities into the Loihi. The Loihi is then generating all of the torques necessary to control the arm here. And because often when we advertise these kinds of programs, you can't just say, because it's cool, we want to do it because it's, it reduces the low, it lets us use low size, weight, and power swap and implement high performance computations embedded in a robot arm where robotic control is one of those problems that is closed loop. Having that low latency, low power embedded solution can also let you improve your performance dramatically. So these are official reasons that we want to do the project. This is the benchmark task. We'll see if this actually runs. Yeah, okay. So it doesn't run, but I can pull it out here. Okay. So this is a simulation of the arm in MuJoCo, and the current orientation and position of the arm is represented by this blue box, and we're just going to randomly generate targets around this like half sphere of the arm, and they're all going to be pointing outwards, and the goal of the controller is just to match the position and orientation of the target. And so this is an example just of what it looks like as it's running. And this task was chosen just as one that kind of representatively goes through the state space and does both position and orientation control. So from those kinds of things, it requires a fairly robust solution. There's a few ways you can do this, of course. We have older traditional like ML methods where you would just have a single large network, you throw it together with some kind of architecture, and you want to input the arm state and a target location, and you want to output the set of torques that you need to actually move the arm to that target location. And this approach can work. It does require a huge state space that you're searching because it's all combinations of arm states and all target locations. These all provide different contexts for the neurons, which need to generalize appropriately across those. So typically it's a huge data set required, or you're using some heuristics or training kind of tricks to reduce that. People like Sergey Levine's lab were doing this years ago. And because we have this like huge state space problem, there's a large network that's required. And when you have a large network and you're not sure exactly what it should be, you have to do this large network architecture search. And so we've got kind of this like exploding problem of both this huge state space and this huge network that we have to search. So it's not ideal is what I'm driving at here. So there's another method, of course, that we can do, or another way that we can do this, because we're coming at this from a top-down side where we know the algorithm that we want to implement. We have, like, this is well documented in control theory. If you want to control a robotic arm effectively and efficiently, you can use operational space control algorithms. And people have shown also that these algorithms match well at a behavioral level to a lot of the performances exhibited by humans. So we can take this algorithm and come at it from a different angle, or sorry, this like prior knowledge, if you will, and come at it from a different angle where we have our equation to start. And very quickly, you won't have to know all of these different terms, but we have our inertia matrices, the M values are inertia matrices. We have our Jacobian gravity, an adaptive component, and then joint velocities here as q dot, and u of x represents the set of forces that we want to apply to the hand. And then u, the actual output signal, is the set of torques that get applied to the arm. And kp and kv are just gain terms, standard PID terms. And so with that algorithm, that equation, we can do this kind of modular approach instead, where we build out exactly as I was saying, the kind of circuit diagram with the functionality that needs to be computed and the flow of information through the network. So if we have our arm, the joint angles q and the joint velocities q dot are fed. So joint angles are fed into this node here, which generates gravity and the inertia matrix term. As well, it's fed into another node down here, which is calculating our Jacobian transpose times the inertia matrix and task space. And then we take the forces we want to apply to the hand, we run them through a dot product with the Jacobian transpose, and we send it to a summation term. Similarly, we just send all of the information through the network to implement the algorithm on this side here. Network is divided into a set of functional components. Each of these functions then is much simpler to learn. For example, this gravity term or this inertia matrix term, these are just functions of Q. They're not, we don't have to send in Q, Q dot, and all of the possible forces that we want to apply to the hand. We just need to memorize the output for all of the Q state space alone, which of course exponentially reduces the size of the problem. So it makes it much more tractable. And additionally, smaller networks are then able to accurately estimate each of these functions, and so it reduces the space, like our network architecture search as well. And so it's just like win, 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 win from this kind of modular approach here. Now, when we're doing this, we're going to do two approaches here. We're going to use machine learning, standard kind of machine learning methods, and we're also going to use what we call the neural engineering framework, which is kind of an analytical approach to deciding or to generating connection weights.
Sorry, Travis, I don't know if you want questions in the middle or you want questions at the end.
Sure. Yeah. No, it's fine. Go for it.
No, because I was wondering how you can get so you're learning gravity here, but how you can learn the gravity from the joint angle. This is something that is very weird from the point of view.
Oh, yeah. Well, so it's gravity is only a function of joint angles.
Okay.
And that's what I'm or what this is representing here is like.
It's not the gravity itself, but how gravity affects to the joint angle. So the input is the joint angle somehow.
Yes. Yeah. So the effect of gravity on each of the joints can be calculated with only the joints angles themselves. So if I know the joint angles of the arm, then I can calculate what gravity is going to be at each position and what torque needs to be applied to each joint to cancel out that effect. Yeah. So that's what I mean here. Right. So any other questions? Also, please, just jump in. I'm happy to go back and forth here. And if not,
I have a question. Sorry.
Shoot.
This modular approach on the slide requires you to have a full specification of the system you want to control. Is that correct? And
yeah.
In the black box approach, which is, I guess we can talk about this later, because somehow there's obviously weaknesses to the black box approach you mentioned earlier, but there must be a middle ground where we don't have a full specification of the system.
Yeah, for sure. Like any vision task, for example, we don't have a top-down, we don't have an equation or an algorithm that we can implement, and so we are restricted to a kind of black box approach. Yeah. So definitely there are scenarios where this doesn't work, but where we have prior information that we can build into the network, then we can do this kind of modular approach.
Great. Thanks.
And so I've highlighted red for machine learning nodes and green for ensembles or sets of neurons that we're going to build out with the NEF, the neural engineering framework. So if we go back to this equation, basically we have these components will be trained or will be generated using standard machine learning methods, and then these dot products will be calculated with the NEF, and this adaptive control term will also be implemented using the neural engineering framework. So implementing the spiking network, assuming that we've gone through, we've trained our networks up. So we have a rate neuron implementation here, and there's nothing particularly tricky about doing that. For the machine learning side of things, we're taking a very standard approach where we have our data set. We take like 10 examples from the data set, some small data set. You find a network that can overfit on this, and then you just start scaling up, right? Now, when you want to implement this in rate neurons, there's a couple of things that come up, or sorry, when you want to implement some spiking neurons, there's a couple of things that come up. The first is that you're going to want to retrain your network with noise in the neuron activation functions, because spiking neurons, the output is noisy, and you want your network to be robust to that downstream, so you add noise to the activation function. The other side of it is we need firing rate regularizers. So for backing up, why are firing rates of the neurons important? If your spiking neural network has low firing rates, then changes in information are going to be slow to propagate throughout the network. If the firing rates of the neurons, on the other hand, are too high, then you end up with minimal temporal sparsity. And from like an engineering standpoint, really the only reason you would want to use spiking neurons is power efficiency gains. And so you lose all of those if you just have like a super high spiking rate. Also, you'll overload the spike routing systems on neuromorphic systems and end up actually introducing latency that way by just having like a huge backlog of spikes that can't all send in a temporally efficient manner. And then another reason why firing rates are important is because the output smoothness of the function depends on both the number of neurons and the firing rates. So I have a nice picture for this. Picture, we have this like simple sine wave that we want to represent in the blue lines here. If we have 20 neurons with a max firing rate of 10 hertz trying to represent this signal, it's relatively noisy. And yes, I don't have axes on any of these plots, but these are all the same axes. These are all at the same scale. And so you can see if we take these same 20 neurons and we just increase the firing rate of each of these to be on the scale of 100 hertz, then it really tightens the representation. We get a much more accurate representation. Similarly, we can also just increase the number of neurons and still keep this low firing rate. It works out to the same thing where we have more information being communicated more often, which allows us to improve the representation at the end. Just kind of as a side note, I also find this as potentially interesting implications for spiking neuron models in general, where you can represent, because like we're constrained to using much smaller models, much fewer neurons that are actually used at any part of the brain, but we can actually generate a similar level of functionality by using higher firing rates. And I'm sure there's some comparison or analysis that comes from that might be of interest. I haven't thought it through fully, so I just wanted to flag that as something I think is cool. And then how do we actually control the firing rates of the neurons? We want to use activation regularizers when we are training with our machine learning algorithms. And typically I've found that there's three ways to do it. You can use a fixed point based regularizer where you look at the average firing rate of each neuron and how far it is from your target firing rate. So if you want to say every neuron should be firing at 50 hertz, then you just calculate the distance from each average firing rate of each neuron. You can do a range based and just penalize any neuron that's firing outside of say 50 to 100 hertz, or you can do a percentile based where you take say the top 1%, the neurons that fire in the top 1%, and then either do a fixed point or a range based. And in our implementation here, we do a percentile range based. So we look at the top 1% of neurons that are firing and then make sure, and we penalize them if they're firing outside of 50 to 150 hertz. So that's on the ML side of things. On the NEF side of things, I'll just explain the NEF very quickly and superficially. But it is essentially an analytic method of, we use population decoding, and it's based on kind of three principles here. We take a population of neurons, and those neurons are going to represent a vector. in vector space. A feed-forward connection between two populations of neurons can perform a function on the represented vector. And then a recurrent connection can implement a dynamical system. And so using these three principles here, we can now implement a whole swath of different functionality and kind of circuits that we have ready to pull out. And so this is an example of some of the different circuits that have been implemented and that we can use. So integrators, oscillators, we can implement associative memory. So if you want to associate colors with smells or something along these lines. And importantly, for what we're going to use here is the product network of the NEF. And this is what our two product networks look like in the context of the actual network that we're implementing. We have our JTMX term from the machine learning trained network, and we have the set of forces that we want to apply. We then send the different dimensions of each of these vectors into a bunch of product ensembles and carefully connect them up or carefully sum the output such that we're implementing a dot product network. And we get, we go from 7x6 matrix and a 6x1 vector to a 7x1 dot product at the end. And then similarly for the other dot product that needs to be calculated between the joint space inertia matrix and the joint velocities. We do this using Nengo, which is a tool for integration. It lets you build neural systems using multiple methods. So as I mentioned, we're taking the ML methods and the NEF methods, and then you can run these networks, each part of the network as a function just in Python in non-spiking rate neurons and spiking neurons or any mix, which is very helpful for implementing this whole process that I've discussed, and just moving from stage to stage. It also has this handy converter from DNNs in TensorFlow and Keras to SNNs. And then when you have a script compiled, you can implement that on a CPU, GPU, or different neuromorphic backends. So this is what it looks like. You have a code programming area, if you'd like, and then more importantly, you have this GUI that you can use for debugging your dynamical systems that you're building up, where you have just a recurrent Lorenz attractor implemented here, the spikes from different neurons in the population, and then in vector space, this is what the represented signal is doing. So that's Nengo. And here are some results from Nengo. So we've taken our network, we've implemented its spiking neurons, and we're running it in our simulated arm, and then we're replotting the results here. And the way that we are comparing or that we're evaluating the performance of the network is we have basically a set of targets are randomly generated and an ideal trajectory to each of those targets is generated, and we just calculate the distance of the arm of the end effector from the ideal trajectory position at each moment in time. So that's how we get our error term that we're using here. And in the dotted, oh yes, sir.
Oh yeah, sorry. You were about to explain your analytic control.
Oh yeah, yeah. So the dotted orange line here is an analytic controller. So just using operational space control and not using any neurons. This is what the trajectory looks like between these different targets. And the blue line is the spiking neuron controller. And then we have
a linear quadratic regulator that you gave the whole model, or how can I imagine this analytic controller?
Yeah, so what we're doing is we're doing PID control in task space, and then we're transforming that into joint space using the Jacobian and the inertia matrices. So the inertia matrices are kind of used to linearize the control of each of the joints, and so you don't have to worry about the Coriolis or inertia effects from any of the other arm segments. And the Jacobian transforms us from end effector forces into joint torques.
Thanks.
Yeah, no problem. And so here we have rows. So this is the X position over time. This is the Y position, Z, alpha, beta, gamma of the orientation of the end effector. And then this last row is a 2 norm of all of these summed together. And so, yeah, we see that we have, there's definitely qualitatively some discrepancies here, but relatively good performance. Formally, it's analytic mode is getting 0.289 and spiking is getting 0.3103, which, I mean, we don't have a reference for these, so whatever. But you can see that it's doing well. But we could do better, probably, if we add in this adaptive term, which I mentioned previously. And the adaptive term is kind of neat in that the training signal for the adaptive term is actually just the first part of the control signal. It is our original control signal, but without gravity compensation, and of course, without the adaptive term itself. And so what we need to do is we just have a set of neurons, and we feed in all of the context that is relevant for those neurons to learn an adaptive control signal. So in this case, it's just the joint angles and the joint velocities. And then we use the training signal to adjust the connection rates on the output side. So high dimensional input encoding, we're using 3,000 neurons in this ensemble, and the learning rule that we're using is the prescribed error sensitivity PES learning rule, which is specific to the neural engineering framework. And this is what it looks like as a result. We have our baseline analytic control, we have our non-adaptive spiking control, and then when we add our adaptive spiking control, we see almost on trial 0, we recover the level of performance from the analytic controller, and then we're able to improve on that actually and further reduce the error or the difference between the end effector position and the ideal trajectory position as more and more trials happen. So that's good.
Can I ask a question there?
Yeah, please. Sorry, I meant to pause there.
Maybe I don't have the right intuition here, but intuitively, why should the analytics? Why should we be able to do better than the analytics?
Yeah.
At all, even with adaptation?
Very good question. I was debating explaining this or not, but you got it. Intuitively, you can kind of think of it as a gain setting kind of issue, where we could, if you had the analytic controller set with gains high enough that it was exactly tracking the target or the target trajectory, then it would not be possible to improve upon this. But here we're actually using gains that are lower just to both ensure stability and so that we can use the same gains across both the analytic controller and the spiking controller. So in some sense, it's artificially setting the analytic performance worse than it might be able to be, but I don't think it's necessarily an unfair comparison. But that's why you can improve over the analytic controller.
Yeah, understood. But then I have a follow-up question, which is the actual adaptive part is being trained effectively on one subpart of the analytic controller, right? What are the gain values that it's being trained on? Are those closer to the optimal gain values, or?
So it's being trained with the same gain values. And what is, like, if you look at the control or the training signal here is just the discrepancy between, it's basically centered around the UX term, which is the difference between the current position and the target position. And so it's being trained to reduce that.
Gotcha. Okay. Understood.
Yeah, a follow-up question on that. When you say high-dimensional input, you mean at the neural level, not at the signal level?
Yes. Sorry. Thank you for specifying that. So actually, in practice, we're not sending in the joint angles and velocities themselves. We're using what's called spatial semantic pointers, and we're projecting those into a high space that makes it such that we have a pocket of neurons that are active in each set of state space and just that part of state space. Otherwise, you can kind of get this generalization effect that happens where neurons are active in one position and another configuration, and these two fight each other. Like, that's what I mean by the high dimensional inputting.
Okay.
Can I also follow up on that? Don't know if you can hear me.
I can hear you. I'm not sure we have still Travis with us right now.
Yeah, he froze a second before also, actually.
Using the semantic pointer lost in the manifold.
Travis,
Hey,
Oh,
Travis.
Sorry about that. My internet is not the best.
I have a follow-up question on this.
Sure.
How does this scale to higher dimensions of the input? So if we go to 4 dimensions, 8 dimensions, 16 dimensions, do you just scale linearly with the number of neurons you need to do this mapping?
Oh, I see.
Yeah.
Yeah, that is a good question. It depends. So to some extent, it depends on the specific problem, like how nonlinear is the space? Can we generalize across similar state spaces? Like some dimensions, you might, if you learn a response here, it might be the appropriate response elsewhere in the state space as well. In this situation, there's not a lot of generalization between different parts of state space, and so as the dimensionality of your problem increases, the number of neurons that you need is going to increase. I would
Probably a
I
lot.
don't know how specifically looked at it, but I would guess exponentially.
I guess, yeah, probably, because you said that you need a set of neurons active in each part of state space. So if your state space dimensions go up, then you need,
And that,
yeah, exactly.
yeah, but that does, if there are any parts of state space that are in, like, if the correction for a dimension of state space is independent of other dimensions, then it's linear. So if we have like this other term, or I can't think of anything off the top of my head, but one part of state space that is the correcting term is consistent regardless of the rest of state space, then it's just linearly increasing the number of neurons that we need.
Great, thank you.
Yeah, no problem.
tell me if that network, it doesn't seem to be recurrent because there's no funny little arrow on it, but
correct.
If you tried that to be a recurrent network, and if, why not?
So you could, I'm not sure what you would gain by implementing it with the recurrent network. There would have to be like, if you wanted to calculate some function of Q or Q dot, like then maybe you would want a third represented dimension that's a recurrent, that is like a function of Q and Q dot, and you're calculating that on your recurrent connection. Maybe you'd want to do that. In all of the situations that I've carried or that I've worked with this in, I'm always able to directly feed in the context that's of interest. And so I haven't needed to use a recurrent connection.
Fair enough. I guess I was thinking of that the recurrent connections would allow us to do arbitrarily fast computations in that population, whereas now you're limited to whatever time constants you have, but usually the ones you apply in Nangham are fairly low anyways and fairly fast.
Right, we're usually operating on like a millisecond time step. I mean, I guess something you could do with this is if you're feeding in joint angles and velocities, you could predict the next joint angle and kind of be a step in the future. But there would be interesting timing things then to work out with the training signal also. So yeah, I'd have to think about it, but I have not worked with it, a recurrent setup.
Thank you.
Yeah, no problem. Okay, so yeah.
It's regarding to the previous slides. It's about
Mhm.
PES. What was the main reason that you choose this one? Because it's you can learn in online methods, or is there any
Yeah.
reason that you have?
Yeah, so basically we're learning it because, or we're using it because it allows us to learn in vector space. We can, it's not, we're using, we're figuring out the contributions of each of the neurons. It just does this extra step where I can calculate the error in vector space and then very easily work backwards to what is the contribution of each of the neurons based on their sensitivities. I know what each of the neurons, so yeah, it's basically because we're using this over another method because we're using the NEF. And so this method works effectively with that, but it's a standard delta learning rule where you're just calculating the error and then doing error assignment to each of the neurons based on we call them encoders, but their preferred directions or what they're sensitive to.
Okay, and then how it would be connected to the recurrent neural network, because you talk about the recurrent configuration. That would be the core learning in recurrent neural network?
If there was a recurrent neural network?
Yeah.
Yes. Yeah, I'm not sure I
because
100% follow.
Yeah, because there we can use backpropagation through the time, for example. And then if we want to keep it in online way of learning, then we can use, the algorithm could be PES. So we can discuss it in this way, that the configuration is recurrent, but the core of learning is PES.
Right. Yeah. So in that case, if we did have a recurrent connection here and a standard PS connection here, then we would be updating the weights based on the neural output at each time step without respect to the history, basically.
Yeah.
Cool. Any other questions? Great. Okay, so the next part, this is briefly talk about implementing the spiking neural network. So let me check my time. Okay, yeah. So converting the network to Loihi, we're dealing with a few things. We need to restructure the neural network architecture first off, because when I implemented this for rate neurons, I'm not worrying about the future. And so I'd use like 20,000 neurons, 2 layers in each of the machine learning levels, or in machine learning network layers. And that is just not possible in Loihi 1 to have that many neurons directly connected, like 2 fully connected layers of 20,000 neurons. The max you can have in Loihi is like 4,000 layers. 4,000 neurons in each layer if you have a fully connected layer here, just based on the memory constraints. Additionally, you have to have kind of this precursor level in front of your network that converts your signal into your input into spikes. And this typically you want to be a small neural network because every spike that you send over increases the latency of the network. And then, as I mentioned, we have to reduce the size of each of the layers. And so as a result, we went from like 20,000 to 20,000 to 3 layers of 4,000. We found was also able to do this task. And then we have to streamline all of the input and output points of the network. And then lastly, the most important part is we need to retrain the neural network using Loihi activation profiles and our firing rate regularizer based on what are the good firing rate ranges for each of these representations. And so what we see here is the standard Loihi standard neuron activation profiles in blue, and the Loihi discretized representations of each of these neurons in orange. And you can see that, like, sub 200-ish on the firing rate side, it's pretty decent representation of the neuron activation functions. But then as you get into larger and larger values, this becomes kind of a heinous distortion. And so what we want to do is make sure that our neurons are all firing in this 50 to 150 hertz range here. And so we do all of this retraining, and we again get a 3D plot of the performance of the network running in Nengo, with, again, orange is the analytic controller or the operational space control, no neurons, and the blue is now running in Nengo Loihi, on Loihi. Looking at this, kind of plotting it again in a different way, we see this is the Z accuracy over time, Y over time, and X over time. And then this is Y plotted against X, Z plotted against X, and Z plotted against Y here. And this, I just find this view helps to assess the performance a bit more quantitatively. If we go ahead and we calculate the discrepancy between the analytic and the spiking controllers, we see there's some slight mean variance, but where we have 95% confidence intervals that almost fully overlap, there's no statistically significant significance between the two, the performance of the two. And this, I feel like this mostly speaks to the paucity of the metric and not the quality of the controller, because, like, clearly there are some, you can see the differences, but kind of measuring performance of trajectory controllers is, it's not, I wouldn't say notoriously difficult, but there's not like a great standard that everyone's using. And so our measure of just distance to the ideal target, to the ideal trajectory, orientation, and position is clearly not capturing all of the features of the movement. But it's capturing some, and along those lines, we're doing pretty well. And then also, because we're on Nengo Loihi neuromorphic hardware, we're also very interested in how much energy is used. What is the cost per inference in terms of joules? And how many inferences per second? Latency and energy, two big advantages offered by neuromorphic hardware. And so in blue, we have the performance of the analytic code, which means there's no neurons involved. It's just running standard operational space control on the CPU. In orange is the CPU running the full spiking neural network. In green is the GPU running the full spiking neural network. And then red is running the network on Loihi. And so we do see here that we get several orders of magnitude gain in terms of energy efficiency, even over the analytic implementation, which I thought was pretty cool. On the inferences per second side, of course, the analytic controller is quite high, 740. When we run the full network on the CPU, we're dropped by an order of magnitude down to 70. GPU is slightly better. And then I run two versions on Loihi here. The first is on-chip, and the second is streaming. And so the on-chip version is basically if the information to send into the network is available, with no delay to Loihi, then this is the speed that we can run at, which is 1200 inferences per second. If, however, we're streaming it, and so you're sending input to the network, running the network, getting the output off of the network, doing a time step on the controller, and then like this streaming loop here, then the Loihi is down at 93 inferences per second, which we've been working with the Loihi since it came out, and this has always been one of the issues. And so it's definitely something that this is not a representative problem for all neuromorphic hardware, and this is something that I've been told has been corrected in the second version, because they had a lot of feedback that originally it was designed for batch processing, of things. And so they weren't concerned about the streaming information, but most people want to use neuromorphic hardware at the edge or for solving streaming problems. And so they've really taken care to improve the bandwidth, I've been told, but I haven't directly worked with it. So hopefully it is actually the case.
So Travis, sorry to interrupt. So
Please.
how you compute the cost per inference energy in CPU, or is something that you develop, or is something that is a standard? And also for the Loihi, in the Loihi, I suppose there's also Loihi on chip, or is the simulator, or how you compute that?
Yes, this is Loihi on chip. And they actually have tools for measuring the inference that they make, or for the power that they make available in the API. And on the CPU and basically all throughout, basically we're measuring the idle power of each of the pieces of hardware, and then the power taken or the power used during inference, and then just dividing that over time to come up with the joules per inference cost.
Yeah, but how this? I mean, but this is it is running only that task in the computer, or you can compute. You can.
Yes. Yeah.
So it's just a single thread or something like that.
Yeah, exactly. And we're running it many, like, this is 100 times we take the mean and then we calculate. They're slight here. It's very consistent, but there are 95% confidence intervals here. But yes, so we run it 100 times. We take the mean of the idle energy cost. We take and then we look at the mean during inference, simulating the controller.
Okay, and in the Loihi streaming, so supposedly, I mean, the bottleneck that you said is because of the interface between the output input. So this is actually it. This is the reduction from 1200 to 93. Is that's exactly that. So there is nothing else happening.
Yeah, exactly.
Thanks.
Travis, can I check questions here on mine as well? Very quickly. CPU, GPU, the timing on those, does that also include that also kind of in streaming mode where you are actually controlling the arm?
Yeah.
Good. And then the other one's a bit off the wall. You mentioned, of course, doing projects like this are also just because they're interesting, right? But in terms of energy efficiency, for a system where you actually know the dynamics ahead of time, do you have any idea how much what an ASIC would look like on a graph like this? I'm just wondering if it's orders of magnitude different, right, or not?
Yeah, that's a great question. I would expect it to outperform the rest, basically. I don't have a great sense of how much what kind of discrepancy, but I would expect that would be the top performance in each of these graphs.
That's also my given everything I know, I would also expect it to outperform, but I'm also trying to figure out by how much.
Fair.
But, okay.
So can I just check quickly, how much more do you want to have in the talk? Because we don't have that much time left, I think. And there's a lot of questions. So I just wanted to check if you wanted to finish,
Sure.
Sure,
not telling you to finish,
I'm asking you how.
Here.
Okay, then continue the question.
Okay, here I'll just get through the last slide quick, and then so in terms of future work, I was chatting with Justice before the talk about this, but we're also taking this and running it on actual Canova ARM, and to do that, so that's what will be happening in the next month here. We've run parts of the network to control the Canova ARM with a Nahuku 8, but we really need the Nahuku 32. So we just got access to this, and I'm pretty excited to have the system fully controlled by the Loihi during this task. We also, you may have noticed I didn't talk about adaptation running on the Loihi board, and that is because there is a couple of issues that crop up. I played with this for a long time trying to get it to work, and it's just too noisy. And part of that problem is because Loihi doesn't, when you connect in training signals, it needs the training signal to come from off chip. And so the training signal is actually generated on chip. And so we get this like, on chip, off chip, on chip again, which introduces both noise and latency. And I think that's, the source of why the adaptation isn't running actually on the Loihi here. So it would be an update to Neko Loihi to get that going. And then also, I'd like to explore this with other neuromorphic hardware. I think functionally, this is one of the more advanced applications that I've seen for spiking neural networks that can run on neuromorphic hardware. And I think it would be kind of fun, or at least interesting benchmark to be used across a few different platforms. And so, yeah, I'm interested hoping to explore that further in some of my work. And thanks for your attention.
Yeah, thank you very much. Just you can take the lead.
Yeah, actually, I'm not sure what your schedule says, Travis. I would have time to discuss one or two things, but maybe I should give some other people the chance to ask their questions first.
Yeah, for sure. Sorry, I didn't realize. I have at least 15 minutes if for questions.
Great.
So any questions?
Just clarification on the energy use slide. I might have missed it. You might have said it, and I missed it. But what is exactly the inference per second measure? Is that the inferences per second that the chip is like? I didn't quite understand that measure.
Oh, I see. Yeah. So yeah, exactly. How many times have I sent input and gotten output from the network per second? And then for the analytic version, it sent the state of the arm and gotten back the torques. Using that across all of them as an inference.
I see. So the neurons are still running a lot in the meantime, also on the CPU version. But if you just look at what do I need to communicate between the CPU simulation of the network and the CPU simulation of the arm, then I can do better than the analytic controller. Do I get that right?
If I just look at the, I see. So the simulation is running lockstep. Both of the simulations run lockstep with each other.
Right.
So yeah. So while the neurons are running, the arm simulation isn't running, and while the arm simulation isn't running, the neurons are running.
Okay, thank you. And also I was wondering about the adaptation not running on the chip currently. This is all Loihi 1, or this is also Loihi 2 chips?
Loihi 1, everything is.
Okay, but then go to Loihi. Yeah, okay. And so, is it possible to actually also implement the adaptation directly into the neural connectivity somehow or something, rather than as an explicit learning signal?
Yes.
Okay.
Yeah. So the Loihi does support native on-chip learning, but it does require a bit of hacking into their messaging protocol, which is possible, but not done.
Yeah. All right. Thank you. Then I just want to thank you for a very nice talk and overview. Thank you so much.
Yeah. No, thank you for having me.
Yeah. Yes. Any other questions, or I can do my question? Or I can do one, and then I leave you just all the questions that you can have. No, I just wanted to say that we are very interested in what you are doing, and we are following you from a long time ago, since I wrote the proposal that we have for the Human Brain Project. Actually, we promised that we will do as good as you or better. This is what we did. That's what we did say, especially with Grace Elia Smith and team. In some sense, we are, and we are trying to catch up to what you are doing right now, and we have different. We are trying in the different ways of research in the learning side, in the non-learning side. Also, Sander is also working with me, and so there are many people interested in Donders at this type of approaches. So maybe one day we will have to present in your lab, or you are still.
That'd be excellent. Yeah.
That's
So
it.
I'm actually full-time at the company, but Chris's lab at Waterloo
Oh yeah, okay.
and Terry Stewart, I'm sure his group would also be very interested to see.
But you're not still working
I
in.
would come.
But you're still working in research, but under the company, I suppose.
Yes. So the work we do right now, like for example, all of this is through contract work with the Naval Research Labs, where they're paying us to perform this work.
I do have a handful of questions.
Thank you, Travis.
The first one, I guess, would be relating. I think this was on your last slide with the energy consumption. This was based on just the energy. Yeah, exactly, that left plot. So there was a computer in the loop at some point as well, a standard PC, even when you use just the Loihi on-chip stuff. Is that correct?
That's correct.
So,
yeah, right now it's the media. Well, even when we have a robotic arm, it's flowing through the computer.
Yeah. And is there a way to set that up without that computer in the middle? Because I can see how right now it's nice to have it technically running on the Loihi and the Loihi itself using very little, compute or energy. But as soon as we are forced to always have that in the loop for the next while, not really able to make use of that very low cost per inference.
Yeah, definitely. So this is again another thing that's basically a matter of wills, or a battle of wills to get this. It is technically possible to set it up so that information is directly streaming onto the Loihi and then directly coming back out. You might need to, they do have a few, I forget exactly, risk cores or something on the Loihi that can handle some of this scheduling and pre or post processing if necessary. But their computational load is quite light. So you might need like a Raspberry Pi to sit there as well. But you can, it is possible to take the computer out of the loop. And they do this with like DVS cameras, for example. They stream that information directly onto the Loihi.
Yeah, that would be a interesting setup for me to see.
Yeah.
Another question I have, maybe I'm not sure you're the right person to ask this, but Nengo and Nengo Deep Learning specifically went to build on top of TensorFlow. And that personally pushed me a little bit away from that. And now that I'm working with spiking networks in PyTorch and use backpropagation through time to train some networks, some of these components that you also had on one of your slides earlier, I think you personally used the dot product one, but there's a whole bunch of nice building blocks that have been developed over the years by various people working with this framework. And I would like to use some of them, but not necessarily. Like, I'm wondering, is the best way for me to just re-implement them outside of Nengo, or are they in some way?
Yeah, so I mean, those are implemented just in Python. And then we have the Nengo DL backend will compile those into a TensorFlow graph. But the very front end of it could be, ported to PyTorch, or worst case, you can take the network structure and the connection weights and just copy those over to be able to carry out the same functionality. I don't think a re-implementation is necessary for that.
Fair enough. I'm going to take a close look at that after the summer at some point. And then I think I'm going to stop the recording here and thank our speaker again. Thank you very much, Travis. Thanks for coming.
Yeah, thank you very much.
Can I ask one more burning question, Travis?
Yeah.
Sorry.
Sure, go ahead.
Sure.
Yeah.
And there always have a lot of questions, so don't think that it's that person.
I'm a little bit stuck on this energy measurement still.
Okay.
I don't understand how simulating a spiking network on the CPU to do a task can possibly be so much more energy efficient in this. If I look at the dynamic energy cost per inference and how many inferences are needed compared to an analytic solution. but maybe I'm stuck in my mind with this kind of just LQR control of a pendulum or something, because there it's so much simpler to do the control of the pendulum normally than in the spiking network, just because spiking network you have to simulate all the voltages, the spikes, everything. So can you maybe say a little bit more about this on what the
Yeah, for sure. So I guess you're looking at like specifically the GPU comparison to the CPU.
No, the CPU, the orange CPU versus the CPU analytic here.
Okay, and you do like note
so
that there's a logarithmic scale.
The per inference is more expensive, but then the number of inference you need for the spiking simulation on the CPU is so much less. And from that, I infer that the total energy use on this is just better with the spiking network simulation.
Sorry, just to make sure that we're clear here, this isn't the number of inferences needed to complete the simulation. This is the number of inferences you can carry out per second.
I see. Okay.
So in this case, the CPU is taking like 15 seconds run to simulate the spiking neural network, where with the analytic mode, it's finishing in like 1 second.
Oh, I see this. I completely misinterpreted this. I thought this was just the number of inferences you need per second to do the task.
Oh, okay. No, sorry. That's my mistake. Yeah.
Okay, now I'm fully on board with this. Thank you.
Okay, perfect. Yeah. No, yeah.
So I think we can close, and actually congratulations on your new kid. Life is a mess, I suppose, because my life is a mess, and Sander probably in some months also. So
no, my baby will be silent all the time.
Yeah, sure. Yeah.
No
Forget about your life, Sander.
I wish you the best with that. Yeah.
Thank you. Justus, thank you very much for organizing this. Probably one day you can go to Travis' company and work there in Canada.
That'd be excellent.
I'll stay.
We expect to be hiring shortly.
Sounds good.
Nice. So
recording now.